And now, everyone's favorite, word problems, where you see how to use all those things you learned in the previous video. So a certain math professor, who shall remain nameless, who is also a foodie, is sifting flour for brownies. The flour forms a right circular cone where the radius is increasing at 3 centimeters per minute and the height is increasing at 2 centimeters per minute. How fast is the volume increasing when the radius is 13 and the height is 18? Well, first let's break this down. What do we know? Well, of course we all remember that the volume of a right circular cone is 1/3 pi r squared h. Now, what can I get from the paragraph? I want to see what the tree structure is so I can figure out what my derivative is going to look like. So I have my volume. Volume is a function of r and h. So I have partial of v with respect to r and partial of v with respect to h. Because v is a function of two things, I use partial instead of derivative. Now both r and h are functions of t. Since it's only one variable, I have dr dt, dh dt. I'm going to try to find the change in v with respect to t. Since that's a function with one variable, I'm looking at dv dt. Using my tree, I see that dv dt is partial of v with respect to r, dr dt, and partial of v with respect to h, dh dt. What other information can I get from the paragraph? I see that the radius is increasing at 3 centimeters per minute, so dr dt is 3. The height is increasing at 2 centimeters per minute, so dh dt is 2. I care about when the radius is 13 and the height is 18. So let me give myself some more room. I need a new slide. So I have this. I've got the formula for dv dt. I've got some of the information I need. I already have dr dt and I have dh dt. I need my partials. The partial of v with respect to r is 2/3 pi rh. Plugging in the values for r and h, I get 490. The partial of v with respect to h is 1/3 pi r squared. Plugging in the values, I get 177. I'm really bad about units. I need to remember what my units are, so I'm plugging in my units. So now I have everything I need for my equation. Let's see what we get. I get dv dt is 490 times 3 plus 177 times 2, which simplifies to 1824. Oh, what are my units again? Let's see, I've got 490 is centimeters cubed per centimeter, and I'm multiplying it by 3, which is centimeters per minute. So I have centimeters cubed per minute. And the same is going to be true for the 177 times 2. Yay. So I'm glad that they're both the same thing, so I'm actually allowed to add them. So I have centimeters cubed per minute. Now, as an American, I have no idea how metric works, of course, because I'm a stupid American. So I want to kind of, what is 1824 centimeters cubed per minute? Well, I know there are 1,000 centimeters cubed in a liter, so this translates to 1.824 liters per minute. And that seems reasonable. I think I can sift almost 2 liters per minute. Yeah, I think I can do that if I'm in a hurry to make those brownies. Let's look at another one. Wow, the sand at the beach today is hot. The temperature at any point is given by T of XY in Celsius. As I try to get back from a day on my beach, my X position is given by X of T is 1 plus T squared cosine pi T, and my Y position is given by 3 plus 2 cosine 2 pi T, where T is in minutes and the position is given in feet. After 3 minutes, the partial of T with respect to X is 2.8 and the partial of T with respect to Y is 8.8. At what rate is the temperature changing along my path at that time? So what do we know? Well, I've got t is a function of x and y are both functions of t. So I have the same tree structure. So the derivative, d big T, d little, yeah, let's just write that one. dt is equal to the part, you can read that. I get tongue-tied when I try to read all these partials and derivatives. Just, there's the formula. So let's see what I know. The partial of t with respect to x is 2.8. The partial of t with respect to y is 8.8. And I want to find out how fast the temperature is changing at t equals 3 minutes. Okay, let's go to the next slide where I have a little bit more elbow room. Oh, and let's put in those units again. So this time I have the partial of t with respect to x and the partial of t with respect to y. I need dx dt and dy dt. For dx dt, I'm going to remind myself that x of t is 1 plus t squared cosine pi t. Taking the derivative with respect to t, I get negative t squared sine of pi t times pi plus 2t cosine of pi t. I'm going to go ahead and plug 3 in for t. Notice sine of 3 pi, we get 0, so that whole thing is 0, so it's gone. Cosine of pi t is -1. Plugging in my 3, I get that the derivative of t with respect to t when t is equal to 3 is -6. Looking at dy dt, I'd remind myself that y of t is 3 plus 2 cosine of 2 pi t. Taking the derivative, I get -2 sine of 2 pi t times 2 pi. And again, my sine gives me a 0, so this whole thing is a 0. Yay! Zeros are good. I like when zeros make a lot of shit go away. So, next page, because this is getting crowded. So now I have all the information I need. Let's see, I've got dt dt. Oh, don't forget your units. I almost forgot my units again. Filling in my formula, dt dt, I get 2.8 times -6 plus 0, which is -16.8 degrees Celsius per minute. Now again, I'm anti-metric girl. I need to figure out what that means. -62 degrees Fahrenheit per minute. So the temperature is changing by 62 degrees Fahrenheit per minute. It's going down. It's getting colder. I think my numbers are not really good for this. I was trying to be creative, but then I didn't pick up the right numbers, and okay, so this is some very strange beach where the temperature is changing by 62 degrees a minute down, and I think if I'd chosen another minute, it'd be going up at about that same rate. Let's try a more standard example. When trying to look up examples for this, I found a box is doing this, and a triangle is doing this, and they were all kind of boring to me. That's why you get the weird sandy beach thing, but it's certainly not boring if I'm on a beach where the temperature is changing at 62 degrees Fahrenheit per minute. Here's one from physics. The pressure in kilopascals, volume V, and temperature T of a mole of an ideal gas are related by the equation P equals 8.31 T divided by V. Find the rate at which the pressure is changing when the temperature is 300 Kelvin and increasing at a rate of 0.1 Kelvin per second, and the volume is 100 liters and increasing at a rate of 0.2 liters per second. So let's see, I've got P is a function of big T and V, and big T and V are functions of time, so we get the same tree structure as before. I need a little bit more space. Let's see what we're given. I see that temperature is 300 Kelvin, and dt dt, another dt dt, is 0.1 kelvins per second. Volume is 100 liters, and it's increasing at a rate of 0.2 liters per second. So let's see what we have here. I know that the partial of P with respect to V is -8.31 T over V squared, and plugging in the values I know, that gives me -0.2493. The partial of P with respect to T is 8.31 1 over V. Plugging in my numbers, I get 0.0831. Now I have everything for my equation. Let's go to the next slide and plug stuff in. And this time I'll make sure to include the units. So I have dP dt is -0.2493 kilopascals per liter times 0.2 liters per second, plus 0.0831 kilopascals per degree Kelvin times 0.1 degree Kelvin per second. So what's happening? My L's are going to cancel, and my K's will cancel. The units for both terms are kilopascal per second. Good, so I can add them. And I get -0.04155 kilopascals per second is the rate at which the pressure is changing per second. So when you're doing word problems, like anything else, break it down into smaller parts. Write down what you know, figure out what you need to figure out, and figure it out. Don't try to do everything all at once because it will drive you crazy.